right, hi friends, we're ready for momentum. We haven't talked about momentum in class, and I'll do a much more thorough video on momentum going in a straight line. But to finish up our rotation ideas, what you need to know about momentum is that every object that has a mass and a velocity has a momentum. This is our equation for momentum. And momentum is conserved, especially when we think about two objects with momentum crashing into each other. So like two football players going to tackle each other. So let's say the quarterback and the nope, that would never happen. My husband would be so embarrassed. The quarterback and the defensive end. I don't know. Quarterback is going to have some initial momentum. Defensive end is going to have some initial momentum. And that's going to be equal to the quarterback's final momentum times plus the defensive end's final momentum. And so these things are conserved. They stay the same. The total value, just like energy, stays the same. All right. So for an angular momentum, this would be symbol L, and it equals I omega. So our moment of inertia times our angular velocity. And so what does this look like? So if you ever have done spun around even, that would work. It's going to be different when you have your arms out as opposed to your arms in. That's changing your moment of inertia. So a lot of times they use the example of a skater. A skater spinning on ice is going to have some rotational speed. And if her arms are pulled in, her moment of inertia is going to be very small. If she puts her arms out, just by simply putting her arms out and changing the moment of inertia, her velocity is going to change. Moment of inertia went up, so her angular velocity is going to go down. And so we can use this idea that initially this skater with her arms pulled in is moving at some speed, and she's going to have an angular momentum, and that's going to be equal to when her moment of inertia when her arms are out times omega, which her new angular speed. And so we can relate this idea of conservation of angular momentum back and forth. We don't really do collisions with rotation. It's more of a how does the moment of inertia change? Okay, and so sometimes they'll give you problems where they give you a mass and a radius and you actually have to calculate the moment of inertia, and sometimes they'll just give you values. So I'll walk you through this one. I would pause it and see if you could do it and then come back and let me explain it to you. Okay, you're back. It says a skater has a moment of inertia of 2.4 kilograms meters squared, and she initially starts with some angular velocity. She pulls her arms in towards her body, changing her moment of inertia. What is her new angular velocity? So we know we're going to use this statement because momentum is going to be conserved. Our initial moment of inertia is given at 2.4. Our initial angular velocity is 5.3. Our new moment of inertia is 1.2. And so we're simply plugging these in and finding a new angular velocity of 8.4. So if we notice, her moment of inertia is going down, and so her angular velocity must go up. It goes from 5 to 8 because it's conserved. So come on in and check out some of the toys I have. I have a rotating platform, and we can put you on it and make you spin and pull your arms in. And it's pretty cool.